Let's take a look at buffer. When you make a protein solution in a laboratory, you need to know how to make buffer solutions with a conjugate acid-base pairs. Commonly used buffer systems for making protein preparations including Tris-hydrogen chloride, MOPS, phosphate, etc. Each of the buffer systems has a working pH range of pKa plus minus 1. This is the example. This acid is Tris-hydrogen chloride. The conjugated base is the Tris base. This is the structure. Eventually, this reaction reach equilibrium. In solution has both Tris-hydrogen chloride and Tris base. Let's take a look at how to prepare a buffer by adding a small portion of strong base in a solution of weak acid to form a acid base conjugate buffer system. Calculating how much hydroxide, basically this is the strong base, is needed for given weak acid. First, we need to make a decision what weak acid concentration is used. For example, 100 millimolar, 50 millimolar, or 20 millimolar. Then, what pH we need? What pH is reached? Then calculate how much strong base is added to the weak acid solution. In this reaction, the weak acid interacts with the strong base to form A minus. A minus is the acid radical plus water. In this reaction, the concentration of weak acid is much more than the strong base. After the reaction of weak acid and the strong base is complete, the system contains three species. The one is the acid molecule of the weak acid, and acid radical and the proton. The species are at equilibrium at the pH, at a given pH. This is the equilibrium equation. And this is a weak acid molecule. This acid radical is a proton. And we use a Hardison-Hatch-Batch equation to calculate the hydroxide. This is the equation: pH equal pKa plus log the concentration of acid radical over concentration of weak acid molecule. At the equilibrium, the hydroxide is completely converted to the acid radical A minus. So the concentration of A minus equals the concentration of hydroxide. Let X equal concentration of A minus or concentration of hydroxide. Then the concentration of weak acid at the equilibrium equal the concentration of acid initial. Subtract the concentration of acid radical equal the concentration of initial weak acid minus the X. After term substitution and rearrangement, we get this equation: pH minus pKa equal log X over the concentration of HA the weak acid initial minus X. Since we know the values of pH, pK, and AH initial, the X value means the hydroxide concentration can be calculated using a logarithm calculator. This is how to determine how to calculate the strong base used for making a buffer with a weak acid. Next, let's take a look at how the buffer setting works. The buffer solution stabilizes the pH by the mechanism called the equilibrium shift. Start with the equilibrium reaction. This is the equilibrium equation. AH form A minus acid radical and plus proton, and the proton and the acid radical can come back to form HA. In this equation, HA and A minus are conjugate acid-base pair. When small amount proton is added, the acid is added in the solution, the equilibrium shift leftward, go this way. And more HA is generated with removing the most of additional proton. When small amount of hydroxide is added in the solution, the hydroxide and proton combine to form the water. The equilibrium shift rightward this way, go this direction, by lowering the proton concentration, generating more A minus acid radical and proton. As a result, not much proton concentration significantly reduced in the solution by adding hydroxide.